Hello everybody, I will start my today's another coding practice. So today's question is this: generate parentheses. So in this question, I'm giving n pairs of parentheses, and I will write a function to generate all combinations of well-formed parentheses. Okay, so let me clarify the question statement first. So I will be given n pairs of parentheses, yeah, like 3 pairs of parentheses. Then I will have 3 opening parentheses and 3 closing parentheses. And from these examples, I can find that there is only single type of parentheses. Yeah. So not like parentheses and bracket or not like that. Only single parentheses type. And also, I will keep reading. Write a function to generate all combinations of well-formed parentheses. So from here, I try to clarify the definition of well-formed parentheses. So let me think of the example when n is 3. So when n is 3, I can use these parentheses, 3 openings and 3 closings. And my task is sort these parentheses and generate well-formed parentheses. And I'm pretty sure this is well-formed. But I would say this is not well-formed. Or this is not well-formed, even though the number of parent openings and number of closings are correct. Or let me think of one more example. So I think this is not good also. Yeah. Because here I can see 3 closing parentheses, even though there are 2 opening parentheses before. So from these examples, I can say that well-formed parenthesis is at any index yeah, so I think this. So at any index, the number of openings must be larger or equal to the number of closings. So let me think if this really applies with one more example. So if I get this, now opening is 1, closing is 1. So far it's okay. And if I put this, not valid. But if I put opening here, this is still valid. And if I opening again, this is still valid. And closing, this is still valid. Because at any index, yeah, it means this condition. Okay, so I've clarified the question statement. So let me think of the algorithm. So in this question, I have to return all the build parentheses. So, I mean, it's not just like returning the count. So I have to build one by one. This means that I have to keep track of the parentheses, which, I've chosen so far. Then I will keep track of them. And finally, if I find the valid one, I will append it to the returned list. So that being said, I think I can use the recursion with the backtracking. Yep. So I think I can do something like, okay, so in the process of backtracking, or I should say the recursion, I should use this chosen so far. So I will append opening parenthesis or closing parenthesis to this list while I'm recursively revisiting the new, recursively choosing the new parenthesis. Yep. And aside from that, yep, maybe I can keep track of the open count software. Yep. Because in each recursive function, like build function, I will try to, take a look at chosen software and decide which of opening or closing I can choose. And for that, I mean, one approach is I take a look at chosen software list every time in the recursive function, but it takes so much time. It takes proportional to the length of the chosen software list. Yeah. So I don't want to do it. So aside from that, I will keep track of the open count software. And with that, I can also immediately know closing count software. So with those being said, I can decide which of opening or closing can be chosen next. I can find the options of the next, choice. Okay, so also obviously I have to return the list. So I will keep this generated list. So this would be the returned list. Okay, so let me get started with the implementation. So I will make this an inner function. Yeah, so this is the scaffold of this my implementation. So I initiated these three variables as I said, and I will call the build function, which is a recursive function, and then inside of it, it generates the list and generates the well-formed parentheses and then append it to the generated list, which is global across the recursive functions. So that being said, I will think of the base case. If I've chosen n, I can say I've found the valid parentheses. So I will create the parentheses, then I will append it to the generated list. Okay, and I will return. And okay, so next thing I will do is I will take a look at close count software first. I will initiate it. Like this. So this is the close count software. And I make sure that close count doesn't exceed open count at any moment. So I would say this, condition is met in the caller side. I don't handle it in the caller side, but in the caller side, I limit the option of the next choice so that this condition is always met in the caller function. Okay, so that being said, so I have to think of two conditions. Number one, open count to close count can be up to n. Number two, open count must be larger than or equal to close count. So if close count solver is exactly n, I have to choose open count. And if open count solver in this case, I will choose the close parenthesis. And also one more thing I have to take care is, in the case I have to choose the open count is that. No, I mean open close is that. If those numbers are the same, I have to choose opening parenthesis. Otherwise, closing parenthesis count exceeds the opening count. And otherwise, I can choose each of them. Both of them are, possible options. Okay. Yep. So these are the cases I have to take care. Wait, but I think I don't have to think of one case. If closing count solver is n, this means that opening, count solver is smaller than the closing count solver. Because if I choose the open count solver n, also in here in line 30, it should be already array returned. Oh, sorry. So in line 30, this should be 2 times n. Yep. So I don't have to think of this case. Good. So let me implement this. I think this implementation, line 45 to 50 is the most easiest maybe. Yeah. Okay, so in this way, I can choose, I clarify the option I can choose next. Then I will choose that option. Then, yeah, I update the parentheses and the open const offer, and then I call the recursive function. And when I come back, I have to roll back the chosen, you know, option because I'm doing the backtracking. Okay. Yep, I think this is it. Okay, so let me quickly walk through my code with n equals 2 example. So if I choose n is 2, in line 57, these variables are initiated first, and then build method is called. And in the build method, in line 37, chosen software ranks is now 0, so I go to line 32. And cross count software is length chosen software minus open count software, so it should be 0 minus 0 is 0. So, yeah, line 43 is correct. And in line 45, open count software is not n, 2. I go to line 47. Open count software is equal to cross count software. Yes, both of them are 0. So option is now only open parentheses. So I go to line 52, and chosen is now only open parentheses. Then in line 53, I will append the open parentheses to the parentheses. No, this should be chosen software. Yep. I will append the open parentheses to the chosen software. Then in line 54, because I chose the open parentheses, so open count software is now 1. Then I call the build method. So I go back to line 36, and now chosen software is 1. So 1 is not 2 times 2 is 4. So this is not correct. So I go to line 42, and cross count software is 1 minus 1 is 0. Yep. So cross count software 0 is smaller than open count software 1. Yes. And then line 45, open count software is not 2. So I go to line 47, and open count software is not cross count software because it's 1 and 0. So I go to line 49. So I can choose any of opening parentheses or closing parentheses. And then line 52, first I will choose open parentheses. Then I keep going. So save my time. I will just check only the open parentheses is chosen case. I mean, iteration step. So I will just see what happens in the base condition. Yeah. So if I choose the open parentheses is appended to the chosen software, and open count software is appended by 1. I mean, incremented by 1. This should be now 2. Then build method is called, and it goes back to line 36. And now length chosen software is only 2, which is not 2 by 2. So I go to line 42, and cross count software is 2 minus 2 is now 0. So line 43 is true. So I go to line 45. Open count software is 2, which is not which is equal to 2. So the only option now I have is closing parentheses in line 46. So I go to line 52 and I have to choose a closing parentheses and I will append it to chosen software. Then open count software is not incremented and I go to build method again and yep. Now I go to line 37. So still it notes the base case. I keep going and in line 45 I find that the only option I have is only the closing parenthesis, and I will choose it. Then open count software is now still 2, because in line 54, int chosen is equal to opening parenthesis is 0, false. And build method is code, and I go to line 37, and now chosen software count is 4, which is equal to 2 times 2. So parenthesis is generated from chosen software, concatenated string, which is open, open, close, close, and generated list. So now open, open, close, close is appended to the generated list. And I will finish the recursive function. Okay, so in this way, I could confirm that, at least I could confirm that it doesn't generate the invalid parenthesis. And also I'm pretty sure that generated parenthesis is appended to the generated list. One case I didn't cover is, lines I didn't cover is line 56 and 57, the rolling back part. I didn't check it. I couldn't cover it because I kept going and didn't backtrack at all. But looking carefully, I'm pretty sure this is correct. So that being said, I'm pretty sure on my code, so I will run my code. I see. So open console for this is not, accessible now. So I added non-local, which makes it possible for the inner function to access the outer context. Okay, so I will submit my code. Good, accepted. So I will quickly do the complex analysis. For time complexity, it should be let me think how many times this build method is called. So it totally depends on the number of valid parentheses, but in a loose upper bound, I will think of the loose upper bound. So in my assumption, I will accept that this is chosen. Not well-formed parentheses, I will accept it, and I will notice it is invalid in the end of the recursion. As the base case. So that kind of, assumption makes it much easier to check, think. So if I do that, the number of possible way to choose is NC3. No, sorry, 2 NC N. I can say from 2 N positions, I will choose the positions where opening parenthesis dominates. They should be 2 NC N. And this is the number of valid parentheses. And also I can say so I built this much, strings That being said, when I choose opening parentheses first, let me write it down. This is one option, but also I have options that here I choose close and then open, close and close. Hmm. Okay, so let me use the condition of this complexity a bit more. So I would say I can choose any of opening or closing 2n times. So let me do that assumption. So in that assumption, I have 2 to the power of n choices. Yep. For each step. So that being said, yes, so the thing is, here I have only one choice. Here, for each one, I have 2 choices. And for each of these open, closer, open, open, I can choose 2 options here. Or I should say this should be 2. So let me think of the number of times recursion is called. So here I have this one is called only twice. But this one, this is called 4 times. 8 and 16 and 32. Yeah, 64. Because I call this second depth function, recursive function, 2 cases. Number 1, I choose the open parenthesis first. Or number 2, I chose the closing parenthesis first. And for each, I have 2 options. So this should be 2 times 2 is 4. And for the third parenthesis, so far until the second option, I had 4 choices, 4 cases. And for each, I have 2 options. The number of times I call this third depth recursive function is 8. So in total, this should be 2 to the power of n. So basically, number of times the recursive function is called is 2 to the power of n. So yeah, assuming that, or I should say, I can say aside from the base case, all of them takes constant time. So O 2 to the n is basic, time complexity, but for the base case, it will take 2n because I'm joining 2n characters. And number of times this base case is called exactly 2 to the power of n because it's the end of the, it's the timing where 2n characters are chosen so far. And the, number of ways to 2n characters is 2 to the power of actually 2n. So it should be 2 to the power of 2n times n. So this n is line 52. So this is the total time complexity of, n times 2 to the power of 2n is the total time complexity of line 52 only. So I guess the sum of them, and it should be O of 2 to the 2 times 2 to the power of 2n. So let me clarify again that this is a loose upper bound because the choice of the parenthesis is limited it should be smaller than this. Maybe in bigger notation, or maybe in the bigger notation, it's the same. Okay. And for space complexity, I use two. I have to think of two things. Number one is chosen software, which is a list, which is up to 2n element. There should be n. And also I have to think of the recursion stack, and number of the recursion stack could be up to 2n. So this should be like this. So I can say the time complexity, no, space complexity is O of n. Okay. So that being said, I will quickly wrap up my today's practice. So today's question was generate parentheses. I will be given the number of pairs. Then I will try to build the valid, well-formed parentheses and return all of them in the list. So I use the recursion with backtracking for this question. And yep, I have to think of the case. So I firstly clarify the well-formed parentheses definition. It should be at any index, count of open parentheses software is smaller than or equal to the count of open parentheses software. So this is the definition of well-formed. And I did the recursion so that it doesn't break this rule. And yep, as the base case of the recursion, if I could choose 2n parentheses in the valid way, then I build the parentheses string and append it to the returned list. Okay, so that being said, I will finish my today's coding practice with this. Thank you so much. Bye.